It is a pleasure to start the session of this morning with Karim Adiprasito, who works in the Hebrew University in Jerusalem. And he'll tell us about Boolean decompositions and Hopf conjecture. Karim, the floor is yours. So we're listening.
Thank you. And if there are questions from the audience, I guess you will relay them to me. All right. I thought I originally suggested something a little more encompassing and a little more general. I decided to focus just on one special case that I think it should be exciting for you. So what is a Hopf conjecture? You probably all remember it. It's we start with a spherical manifold. All right. So M, a spherical. Closed, so the usual words: closed, compact, orientable, of dimension n. All right, then the conjecture is conjecture, and then there are different versions, and it differ somewhat in attribution. Somehow Thurston is a name that you throw in. There's churn. But also, most of all, it's Hopf. And the conjecture is that if I look at the Euler characteristic of this manifold, then it is of sign, oh, let me write it like this, times -1 to the n half is larger or equal to 0. Of course, if n is odd, I don't care, right? I just throw it away. Then the Euler characteristic is 0 anyway. But in all the other cases, right? In all the other even cases, this is a very interesting conjecture, and I think it's very mysterious. Most of all because very few people understand what a spherical means, right? I mean, not only, most people know the definition in some way, right? A universal cover is contractible, but I don't think anyone really understands what it implies, because there are many conjectures around the spherical spaces, even like a Whitehead conjecture for two-dimensional spherical spaces. So it's a very mysterious conjecture. So what do we usually do, right? So if we don't understand something, maybe there's a simpler class that we can understand. And then the geometers usually enter the picture and make the observation that if a complex, if M is okay, so let me say non-positively curved in the Alexandrov sense, or in the sectional curvature, right? If you prefer smooth spaces, then M is aspherical, right? So that's useful information. So now this turns, this immediately gives you a geometric handle on this problem, right? That's much easier to understand, having non-positive curvature. But still, the conjecture is open, and there's not much known. Okay, so this still open, even in this case. Even if this case is open. Okay. Okay, so I mean, if we can't solve that case, maybe we can solve another. So how do I come up with spaces of non-positive curvature, right? So examples for non-positive curvature. Well, I mean, for instance, I could just take something hyperbolic, right? That would be nice. So I could take some quotient of hyperbolic space as compact. I could just take a quotient of Euclidean space, but of course these cases are boring. So, I mean, these kind of homogeneous, these very homogeneous spaces they're automatically true. Okay, just because of Atiyah-Singer index theorem. There's nothing to do there. So let's construct something more interesting. So let's, I mean, I usually come from combinatorics. So let's construct some combinatorial examples. So how would I build something of non-positive curvature? Well, what I could do is I could just like start somehow with 4 squares around the vertex, right? And then I could just continue this whole process. Right, you see that this is locally Euclidean, so surely whatever we'll get will be non-positively curved. I could also have started with the following homogeneous space, right? I could start with 5 of these squares around the vertex, and every one of these squares has the metric of the unit square, right? So everyone here is just the metric of 0, 1 square. Okay, nothing fancy there. All right, so what is the general recipe? All right, so this is Davis and Mousson, given any flag triangulated sphere, there exists a cubical complex, a cat0 complex that looks everywhere like this. Let me name the sphere here. Let me call it sigma, like sigma. So example would be, right, I have this is a triangulation of the one-dimensional sphere. Right, and if I look around every node here, around every vertex, I look like this one-dimensional sphere. Here I have a similar observation, right? If I look at the 5-gon, okay, and this 5-gon, somehow you find it around every of these single ones of these vertices. You can continue here. There will be another five squares around this vertex, and so on and so forth. All right. So that's the idea of the construction. And so the point is then, whenever I have a flag sphere, so now whenever I have a flag sphere, sigma is a flag sphere, we obtain well, okay, so it's a spherical manifold, but it's non-compact, and a spherical manifold. Let me call it M tilde of sigma. Okay, and you can now ask, of course, well, is there a compact quotient? And is the Hopf conjecture true for this manifold, right? For this quotient. So the quotient is, I mean, it's not obvious that there is a compact quotient, but if you think a little bit, or then you see that there is a natural one, because to this sphere sigma we can associate a group. Okay, so sigma is associated to a group as follows. So I look at the graph. So G is the graph of sigma. And now I look at the group gamma of sigma. And this is generated by the vertices. So I have a generator for every vertex. And I have two observations. So I have that every vertex square is equal to 1. And I have that a commutator relation whenever two vertices are connected by an edge. If VW is an edge. Okay? Okay. So, for example, right, I had this manifold that looked locally like foregone earlier, right? And the group associated to it has 4 generators, 1, 2, 3, 4. So I have generators V1, V2, V3, V4. And each of the VI's square is equal to 1. And I have VI plus 1 is equal to VI plus 1, VI. And that's my group. Okay? So this is okay. So this does not act quite so nicely, but if I take the commutator of this group, so I take gamma of sigma, this acts properly and co-compactly on m tilde of sigma, and I can take the quotient, and this is compact. It's a compact manifold of non-positive curvature.
How does gamma sigma act on?
All right? And okay, so now I can ask, of course, is it the conjecture true for this case? Is the Hopf conjecture question, and this is usually attributed to Charney and Davis.
Can you say how gamma of sigma acts on?
So Alex Suchu always says he has a hand in formulating this. Is the Hopf conjecture true for these manifolds?
Karim,
Yeah.
can you say how gamma of sigma acts on m tilde of sigma? I would have thought there are many choices of m tilde of sigma if like sigma sort of doesn't have any symmetries, and there are many flag spheres. Well,
Okay. Okay, so I should have probably. Okay, wait a second, and I will give you a direct description of this quotient, okay? And then you will see it, okay? Thanks for the question. Okay. All right. So okay, so maybe to let me give a direct description of this complex modulo gamma. Okay, so it's a compact. I want to have a compact cubical complex that everywhere, such that at every vertex I look like sigma. And here's here's a construction, and it works for any simplicial complex. So I start with delta any simplicial complex. Okay. Now, what I want is a cubical complex that is compact and looks everywhere like delta. That locally looks like delta. And here's the construction. Let me say that this this simplicial complex has n vertices, okay? On n vertices. Okay. So how do I do this? Well, let me look first at Cn, the n-dimensional cube. Okay. And I want to construct this as a subcomplex of this cube. Okay. What I want is a subcomplex of Cn. So let me just visualize it. So let me make an example. So let's say I am in the case n equals to 3. So let's say n equals to 3. I look at this cube. It's spanned by well, it's a cube 0, 1, 2, 3 in R2, 3. Right? And I just identify each of the coordinate directions with one of the vertices. So let's say my complex in this case has 3 vertices, 1, 2, 3, and I have 3 coordinate directions, 1, 2, and 3. Okay, and now I have my cube on these vertices. And now, okay, so what do? I do the following. I take dancer of sigma. Oh, sorry, I did this for delta now. I wanted to do this for general complexes. Dancer of delta, so d of delta, is defined as those faces tau in Cn, such that if I take the affine span of tau, this is parallel to the span of sigma for some sigma, little sigma in my simplicial complex. Okay, so what would it be in this case? So I identified the vertices with the coordinate directions. So I have to, okay, so I have one of the simplices in this complex would be this vertex, right? So I have the span of, well, just this vertex, so it would just be the line. All right, so I have to pick up everything that is parallel to the line. So I have this, and this edge. I also have this simplex on 2 and 3, right? So again, 2 and 3, they form a simplex. So I look at the span. The span is exactly this hyperplane here, all right? So what do I get? I get this face, this part of the cube, and I get this part of the cube. All right, and you see, if I color this a little, if I look from the viewpoint of any of these vertices, all right, from the viewpoint of any of these vertices, I look like my original complex. All right, and that's it. All right. So this gives me a compact space. It's a direct description of this. This is a direct description of this quotient. Okay. What is the action of this group? Well, if you think about this, this really acts by reflections. So I can go back perhaps. So what is the action of every element in this? Of every element, it acts well. I mean, if I stand at this point, right? So this point here, and I look in this direction, this corresponds to a vertex in my graph, and the action corresponds to a reflection on this hyperplane. Okay, so I act by reflection. So in particular, the name for these objects here, the name for these groups, gamma of sigma, are just the right-angled Coxeter groups. Gamma and sigma are known as right-angled Coxeter groups. Okay. All right. So what is the how do I attack this how do I attack this conjecture then? How do I even how do I get back to the Hopf conjecture? All right, I can now compute the Betti vector. Right, the Betti vector, it's of this somehow. I compute D of sigma. All right, this is the Dancer complex. This is again the same as the quotient that I described, and I can compute the cohomology ring of this. And this has a Betti vector, and this looks like something like 1, 7, 27, 1. Okay, that's the space that I'm looking at. And now, what would be a good way to think about the Euler characteristic? Well, here's one idea that is due to Sviatoslav Gal and in parallel Peter Brenden. So what they do is basically they decompose this into they decompose this vector, this Betti vector, into vectors that they understand, and only one of them has a non-trivial Euler characteristic. Let me give the example. So how about I decompose it into the following vectors, 1, 4. Right, I just take rows in the Pascal triangle. So just these the binomial coefficients with a fixed number of elements, and I shift them appropriately so that the middle coincides. Right. So there's a unique way of writing. There's a unique way of writing this here in terms of binomial coefficients, right? In terms of binomial coefficients. Right? In particular, in this case, it would be, right? I can take this here once, then this here 3 times, and this here 8 times. And if I sum up these vectors, then I get the vector at the top. All right, so 1 this plus this plus this. Okay. And now what do you see? Well, if I compute the Euler characteristic of any of these vectors, the Euler characteristic of this is 0, the Euler characteristic of this is 0, and the Euler characteristic of this is 1. So what the conjecture, what does Hopf conjecture say? Well, Hopf conjecture says that this, when I write this in terms of these vectors, this number here is non-negative. And then the conjecture became more generally, so conjecture of Brenden and Sviatoslav Gal in parallel was these coefficients here that they call gamma of sigma. So they start with gamma 0. This is gamma 0, gamma 1, gamma 2. All of them are non-negative. Gamma I are non-negative. Okay? So how do we prove that? How do we attack that? So how could this be attacked? Well, let's remember something from algebraic geometry. Okay, there's a kind of similar decomposition that somehow that every algebraic geometer knows, and this is the Lefschetz decomposition. All right, in the Lefschetz decomposition we have a kind of similar phenomenon. So again we have 1, 7, 27, 1, and then what I do, right, I decompose this on a purely numerical and very naive level into vectors of the form 1, 1, 1, 1, 1, and 1. All right. So what does this? How does this look? Well, I mean, in this, let me to distinguish it from the cohomology ring. Let me call this ring A of some variety. Okay, so A of X, and what do I want to say? Well, A of X is really isomorphic to a direct sum of some spaces P, right? The primitive components under some Lefschetz element, Pi times. Okay, so now let me work over arbitrary characteristic. I have some field K and a polynomial ring X, and then I take out. Okay, okay. Let me assume that all degrees vanish. So I'm in toric variety, for instance, just to make the correspondence nicer. So then I have a polynomial ring in one variable, and I take out X to the d minus 2i plus 1, and that's it. Okay, so I have these shifted copies of what? Well, I mean, this is a cohomology of a projective space, right? So shifted copies of the cohomology of projective space. Okay, so what would be the analog of this kind of beautiful this beautiful and very famous and very important decomposition that in some way tells me something about about the Hopf conjecture and this Brenda-Gall conjecture? Well, I could try to do a similar thing, right? I can try to write H as, well, the direct sum of some spaces Bi. I should say here Pi is a subspace of the ith graded component. So I write this as a direct sum over Bi, and then tensor I, and then what I have here is some exterior algebra. All right, so I have okay, so I want some alpha, so alpha 1, alpha I are elements in H1, and what I want is alpha, sorry, I j equals 1 to d minus 2i, and then I have to get alpha j here. All right, so I have this, I have alpha I, and then the bi's are subspaces of hi, and that's what I want, and I call this Boolean decomposition, or exterior decomposition, or torus decomposition. Right? So why torus decomposition? You should think of what happens here as embedding projective spaces, right? And what happens on this side, I kind of embed, I decompose into cohomology of tori, right? Okay, so how to proceed? All right, how to proceed? Well, I mean, the natural thing would be, all right, well, does H have, so H of, let me be specific, H of D of sigma have a Boolean decomposition? And if that is true, then immediately we get the Hopf conjecture. Okay? I mean, immediately get the Hopf conjecture in this case. Okay? And I want to basically tell you that this is true, at least in a few cases. And perhaps it is true in general, but I don't know yet. Okay, so theorem. This is true for sigma a flag PL sphere and cohomology with let's say with characteristic zero coefficients, so with real coefficients. And the second case for arbitrary characteristic, well, almost arbitrary characteristic that is not equal to 2, and sigma balanced and flag. Okay. So maybe, I mean, I have to explain what balanced means. Balanced means that okay, so this is let's say of dimension d-1, and balanced means that the vertices of sigma have decoloring. Okay, so let me give an example to explain. So here would be a flag sphere that is not balanced, right? Because why is it not balanced? Well, so it's a d-1, so it's a one-dimensional sphere, but the vertices don't have a 2 coloring. So if I say I color this with color 1, 2, 1, 2, then I have to, okay, so then this, I mean, that tells me that I have to use color 1, but you see that then this edge is monochromatic. That's not what I want. If I give this color 2 though, right, then I get a conflict down here. So it's not balanced. So these are the two conditions under which I can prove it. I conjecture that this is true in general, but I don't have a proof yet. Okay. Now let me give you the intuition of how this works. Okay. So ideas. So what is going on? So let's observe a few things. So let's say I have a map of simplicial complex X. So delta so some facts, all right, some facts, observations, or whatever you want to call them. So if I have a map delta of simplicial complexes, delta to delta prime, let's say. Okay, so for instance, I could have a map of this 5 gone to, well, I could contract, for instance, this edge here. All right, so I have a simplicial map from delta, from the 5 gone to the 4 gone. Then this induces a polyhedral map of d of delta to d of delta prime. So it induces a map of these dancer complexes. Okay, simple observation. So in other words, this behaves nice with respect to deformations of dancer complexes. Behave small. The dancer construction behaves nice with respect to this deformation. In particular, I obtain also a map in cohomology H delta prime to H of delta. Okay. And if these are spheres of the same dimension, so if delta prime flag d-1 spheres, this is an embedding. This map is injective. Okay. All right. So that's one fact. Let's see some basic manipulations of simplicial complexes. So here's another useful observation. If okay, so let's look at what happens if I look at H of delta or HD. Let me just write it like let me not even look at the cohomology. Let me look at the difference between D of delta and D of the suspension of delta. All right, so example would be I have delta, these two vertices, and the suspension would be this. All right, I have 2 points that I add and I cone on each side. That's a suspension. Then, so what happens? D of delta. So, well, on the level of the dancer complex, this is the D of delta times S1. Okay. So what else? Now I have to give you 2 non-trivial propositions. So it's somehow now these things become a little bit more tricky. So let me first, okay, so let me leave some space for metaphor. Okay, so and let me state the 2 propositions. So proposition 1. The cohomology ring of D sigma is what some people would call standard. It's generated in degree 1. Okay, so in other words, everything of positive degree is a product of elements of degree 1. That's already a rather rare property. It tells you that there's a lot of cohomology, right? Proposition 2 is okay. So I earlier wrote this. Okay, so I had this. I had this map for from delta. Okay, so I had a map from delta to delta prime. Let me look at some special maps. So I could look at sigma, and then if sigma bar is codimension 1 induced sphere, well, then what I have is a map from sigma to suspension of sigma bar. So in particular, I have a map from the cohomology of the suspension of sigma bar into the cohomology of sigma. All right? But I don't want a map that is just an embedding. I want a surjection. So I could hope that maybe I could hope that something like this is true. Right? I want to cover this with spaces that I understand. So it's a suspension of sigma. So what I do is, okay, so I could hope that if I sum over all sigma bar codimension 1 spheres, then this map here is onto. It's unfortunately that's not so simple. I have to take a little bit more. I have to take cycles here, and I have to kind of and also I forgot to write again that this is the dancer complex. Sorry, I'm talking about the dancer complex. So I have to sum over all induced cycles. Induced codimension 1 cycles. Okay. So why is this in particular useful here? Okay. So why does this come in? So where does this come from? Well, the idea is okay. So the idea is to use induction in a clever way. Induction. So if the cohomology of the some codimension 1 cycle here has a Boolean decomposition, then so does the suspension. Okay. Now, proposition 2 then tells us that then h d of sigma is covered by it's covered by subs by exactly actually it's subrings by subrings that have a Boolean decomposition. All right. And then what you want to hope is that in this somehow, in some clever way, this leads to a Boolean decomposition for this cohomology ring. Okay. That's a hope. That's what you want to do. Okay. And okay, so why are these two propositions true? So let me why. Okay. Okay. So let me. Okay. So that this is somehow this is the approach for the balanced case. And proposition 1 is needed in the proof of the PL case. Is needed for PL case. PL case. And there the idea is essentially in the PL case, we know that somehow all the flag PL spheres are connected by an element by a sequence of elementary mutations, and you want to track what happens to the Boolean decomposition along this. Let me not go into this, but let me try to give you an intuition of why these two propositions are true. Okay, so why do the induced cycles generate the cohomology, and why let me try to give you the intuition of why do the induced cycles give generate the cohomology, and then why do I have this generation in degree 1? Okay, so let me give an notation. So, idea for proof of proposition 2. Well, I mean, it's in the end, it turns out to be rather simple. So what we want to say is that in some way, totally geodesic cycles generate the cohomology. Okay, so that's all we want. And the idea is rather simple, and almost embarrassingly so. Okay, so I have my cube, all right? This is my dancer complex is a subcomplex of that cube. And then I have some simplicial cycle here. All right, something like that. Okay, so this is a one cycle. All right, and now what I can do is I can just lexicographically order the vertices of this cube that supports my dancer complex. And I can one by one symmetrize them, right? So this, in some way, I just what I look is I look at the vertex here of the cycle. I look at its link. These are these two vertices here, and I look at the dancer complex of this, the dancer of the cycle. Right? So the dancer, this dancer map, it doesn't only work on complexes, it works on cycles as well. And you see that then I get this symmetrized cycle here. And so in other words, if I take this top cycle away, then what I'm left with is a new cube with a new cycle, where now this vertex here is removed, and the new cycle is just the cycle on these vertices here. And then I repeat this process here, and I decompose it into this cycle and this cycle. And finally, I'm done with this. Okay, so this is, I just decomposed it into new cycles, and that's it. Now, this also tells you rather something nicely. So that it tells you that in some sense, the intersection theory of the entire intersection theory of cycles in D, so intersection theory in the dancer manifold, D of sigma, is intersection theory, or write it in, so cycles in D sigma is intersection theory in a purely local way in sigma, but not somehow you have to be careful, because I don't pick only the homology cycles in the sphere. They're boring. But what I take basically intersection theory of all induced subcomplexes. Okay, so what do I mean by that? All right. So here's my flag sphere. All right. And let's say I want to understand this proposition 1 a little better. All right. I want to say that every element is the product of codimension 1. Codimension is a product of cohomology cycles in dimension 1, or in other words, every cycle is the intersection of codimension 1 cycles. So what does a codimension 1 cycle look? So what does a nice low dimensional cycle look like in this flag sphere? Well, if I look at a one cycles in D of sigma are generated by induced cycles in sigma, induced zero cycles. Okay, so here's a zero cycle. All right. And now, how do I think about this? I mean, how do I prove this claim that this is an intersection, that the corresponding one cycle is an intersection of codimension one, so two cycles in this three-dimensional manifold? Well, I want to look at induced one-dimensional cycles, right? Two cycles in the manifold correspond to one cycles in this object. So I want to have this as I want to write this as an intersection product of this cycle and this cycle. And you see that it is possible, right? So I have these two cycles, intersect them in some stable way, and I get my zero cycle, which in particular implies that the original two cycle that the original one cycle that I had in D of sigma here is the intersection of two codimension one, two induced, two totally geodesic two cycles. And that kind of gives you a flavor of the proof. So in the end, you reduce it to an intersection theory in sigma, right? In this flag sphere. And this, it turns out that we understand it rather well because we understand these are essentially things modeled by Stanley Riesnering. So this is the whole subject of combinatorial commutative algebra and combinatorial Hodge theory. And that we understand this in the end gives us the proof of these special cases. So this is a kind of interesting reduction to Lefschetz theory. So let me close to, in the end, so what the cases that we can prove reduce to Lefschetz theory. So these cases reduce to Lefschetz theory, to proper Lefschetz theory, right? I think of this, you can think of this Boolean decomposition as like an anti-commutative analog of a Lefschetz decomposition, but now you reduce to proper Lefschetz theory. Okay. What is nice in the case of the Boolean in the case of the original Hopf conjecture is that there is another case that we know from Lefschetz theory, and this is the so-called this is a case that was explored by Gromov, that if I look at not only hyperbolic manifolds, but if I look at manifolds that also have a Kähler structure, right? So not positively curved, but with a Kähler structure, then I also get it, right? So another connection to Lefschetz theory. To Lefschetz theory is due to Gromov, right? Who looked at the case when it's the opposite of this polyhedral case. He looked at the case when you have Kähler structure. Or Kähler implies. So I wonder whether there's something deeper there, whether in some way, if one uses the techniques that are developed for combinatorial Lefschetz and Hodge theory in a more profound way, then you can end up with a full proof, a proof of the full conjecture. At least maybe in some, I mean, I don't know whether I believe it for a spherical, but maybe some more interesting cases that come from geometry. That's where I wanted to end the talk. I apologize, it's pretty open-ended, but I hope that somehow at least there's some impulse. Thank you.
So is there any question, comment? Let me know, Karim, if you get a question.
Can you hear me?
Yes, yes.
Okay. You are saying that this Boolean decompositions are somehow similar to Lefschetz decomposition, but
Yeah.
then precisely why they're similar?
Well, for one thing, I did explain small what I explained was this way that Lefschetz decomposition decomposes you into copies of the cohomology of projective space, and now I decomposed into into copies of the cohomology of tori. Here's another way, right? There should be some Lefschetz isomorphism, right? So if I look at H0 and HD, then there is an isomorphism that is induced by alpha 1 to alpha D. I take the product of them all. Okay? This is an isomorphism. And now I can look at all the intermediate images, right? I can look at all the images of subproducts, right? If I look at all the intermediate images, then this is, this is essentially just B0 times the exterior algebra generated by these alpha i's. Right? Or let me do it alpha j. Now, okay, so I can take, this is a Poincare duality algebra. I can take the orthogonal complement of this. I can take the orthogonal complement and intersect it with H1, and I obtain a space B1. Okay, so let me denote this by B1. So I have B1, and I can also intersect it with HD minus 1, and I obtain BD minus 1. Okay? So I have B1 and BD minus 1. Okay? And again, I have an isomorphism between these two, induced by the multiplication alpha 3 to alpha D. So I forget the first two, and I have a multiplication of these. And then I can iterate, right? I can take the orthogonal complement of this with respect to the Poincare pairing, and I obtain B2 and BD minus 2. And I have an isomorphism alpha 5 to alpha D.
But each time the subset of alphas is decreasing, right? Or
Huh?
the set of alphas is changing every time.
No, you don't have to change it. So it's the same set of alphas. I just pick two less.
Okay.
You can show that it's more. Okay. So you could think of cases where they change, but you can show that it's more generically. You can always choose them the same. Okay.
Any other question? Well, if not time, thank you very much for the lecture.